by dt of dr by dt, that is L prime mr square into dr by dt. Okay, so this 1 by r square, this 1 by r square into dr by d theta is minus du by dt. If I write like that, 1 by r square into dr by d theta, 1 by r square into dr by d theta is du by d theta. So this m I will pull out, m will cancel. So it will be L d by dt with a minus sign du by dt. You understand that? Now again d by dt is minus L square by mr square into d by d theta of du by dt. So this is equal to minus, I will write, see here I am using 1 by u as r. So this is minus L square u square by m into d square u by d theta. So second derivative calculation, d2r by dt2 is given by this. On the right hand side we have f of r, that is RHS, right hand side. We have f of r plus L square divided by mr, which I can write as f of 1 over u plus L square u cube divided by L square u cube divided by L. As a result, the equation for the orbit can be written in the following form, that is minus L square u square divided by m d square u by d theta square is equal to f of 1 by u plus L square u cube divided by m. So if I take this on the other side, I have d square u by d theta square is equal to minus m divided by L square u square into f of 1 by u minus L square minus u. In other words, we have an orbit equation d square u by d theta square plus u is equal to minus m divided by L square u L square u square f of 1 over. So this is called equation of an orbit. So given a force, some force law is given, then you can calculate, you can obtain the orbit by solving this differential equation. Okay? So given f of r, we can solve with above ordinary differential equation. In principle, to get u as a function of theta, which implies r as a function of theta. But usually we don't do it this way, because doing this is a little more difficult. But sometimes we will have problems where we know the orbit, by some observation. Like Kepler knows the orbit. And we would like to know what is the force law. Then this is the easiest because we have to simply differentiate. So if you know the orbit, if you have to find out the force, let's say you know the orbit by some observation and you want to find the force law, then this is the best equation to do it because you have to simply differentiate it, then you get the force law. So there are two ways, two things. Given the force, find the orbit. Given the orbit, find the force. So this orbit equation is most useful for finding the force given the orbit. If you are training some students for these competitive exams like CSIR, just kind of exams, this question is usually asked. An orbit will be given, you have to find the force. And for that, you should use this equation. Now, how to find the orbit? So let me say that even though this is in principle said, but this is used for the differential equation for the ordinary differential equation for the orbit is best used to find force f given r. Some problems like this you will see in the tutorials. How to find the force law given the r. So this is best used for that sense. How to find the orbit? That is what I did in the morning. So to find the orbit, for the given force and potential, we go back to the quadrature. As I wrote in the morning, we have dt is equal to dr divided by square root of 2 by m into e minus v effective of r, and d theta is equal to L by mr square into dt. Together we can write down d theta is equal to, so I can write down this L by mr square into square root of 2 by m into e minus v effective into d into dr. So this equation can be more generally written, or this equation can be modified to write it in a sensible form. If you look at this expression, we have d theta is equal to dr or LdR divided by square root of This m, if I take it inside, it becomes m square. So twice m into this quantity. I also take this r square is also inside. mr square. Okay, let r square be outside. So let me see r square like this, and then I have twice m into e minus v of r minus L square by twice m r square. Now if I pull out L square out of all this, if I pull out L square, then that L will cancel with this L. This is equal to dr divided by r square square root of twice me by L square minus twice mv by L square v of r minus 1 by r square. This is your dt. Now you substitute u is equal to 1 by r, then du is equal to minus 1 by r square dr. Okay, so now you can write this as d theta as minus du divided by square root of twice me by L square minus twice mv of u, in this case by L square minus u. You can call it v of 1 by u. So the orbit integral and the quadrature for the orbit, you can know the recast. So if I call theta naught as the initial condition, then theta minus theta naught is equal to integral from u naught to u. Okay, u naught to u, and that I can write it as theta as a function of theta is equal to theta naught minus integral from some u naught to u du prime divided by square root of twice m e by L square minus twice m by L square v of 1 by u minus. So if you can integrate this for a given u, you will get that. Okay, so by integrating about expression, we get the object for given So conventionally this is easier, and that is what Naina has shown in the morning in one problem. But so he has shown V of r is equal to minus k by r, which is equal to minus k times q. Okay, so this was done in tutorial 1 and 1, and we showed the equation for the given force. So if you want to find the orbit for a given r, we can use this quadrature. And if you want to find v or f for a given orbit, then you use differential equation. Okay. There is no hard and fast rule. You can also use this to find the orbit. maybe it will become difficult. That's all. To solve the general second order inhomogeneous equation, and there are methods to solve such things, and that's also possible.
So the choice of constant.